Okay, so we are in section 4.1, like I said. This is extreme values of functions. All right, so basically our goal in this section is to find the, if you're thinking about it in terms of a graph, the highest or lowest point on a certain interval. Okay, so we can't do it if we just let it go necessarily negative infinity to infinity, because depending on how the graph might look, it might just keep going up or it might just keep going down and that sort of thing. So anytime we're talking about extreme values, or at least most of the time, we're going to be talking about it on a given interval. Okay, so I'm going to start by defining that a little bit more succinctly in the kind of math speak here. So definition of an extreme value here. So we're going to say let f be continuous with a domain D. All right, so just some function with a domain of D. Then f of c. Okay, thank you. Then f of c. Oh, don't get fuzzy on me. That's better. Is the absolute max if f of c is greater than or equal to f of x for all x in D. And it's an absolute min if f of c is less than or equal to f of x for all x in D. Okay, so basically it's the biggest, the value of it is the largest compared to everything else in the domain, or it's the value of it is the smallest compared to everything else in the domain. I'm going to try and reset this here in a second to see if I can get this a little clearer. That was pretty darn fuzzy still. I might just have to get a new document camera at some point here.
Did you just give those out now?
I got a few sitting around. I don't know if that's any better. I don't know. We'll go with it for now. I wish that was better. So, okay. Now, there's two different kinds of maximums and minimums that we're going to be looking at. The absolute max and absolute min is exactly this. It is the highest or lowest point in a given interval or on a given domain that you have. We also have what are called local, maxes and mins, which would be just kind of like in the neighborhood. So this would be the largest or smallest value of a function compared to the points around it. I'll show you an example of this. So, like if you have a function where it kind of goes up, hits a maximum, comes back down, but then maybe turns around and keeps going again back up, it might not be the highest point on the function, but it compared to the little points that are all around it in that area, it's the highest thing there. So then we call that a local max. Okay? So I'm going to draw you a little graph here, and I'll put some local and some absolute maxes and mins on there so you can kind of see the difference here. So let's say that's our function. Okay. Now, can you guys see how we have two maximums and one minimum on there? All right. Is that obvious to y'all? Right here and right here, those are your two maximums. And then right here, that's your minimum. Okay. Now the question is, are these just local max or mins, or are they absolute max or mins? Okay. So this first one right here, how would we identify this maximum right here? Is it local or is it absolute? That's definitely just a local max. Yep. Okay. And then this point right here, how would we identify that? It's a minimum. Is it a local minimum or an absolute minimum? Be careful. It's just local. Why is it just local? It's because of this. What do these little arrowheads indicate? Still goes down, right? So this, because these are going down both below this would just be a local min. And then how would I identify this point up here then? Absolute max. Yep. So this is an example of a particular function that has no absolute minimum then. Okay, if these two sides continue to go down to negative infinity both times, then you're not going to ever have one point that you can identify that is an absolute minimum. Unless we took this thing and chopped it up on some interval and said, okay, now we can consider the endpoints as being maximums or minimums and that sort of thing. Otherwise, yeah, you wouldn't have one at all. Okay, so that's kind of the difference for that. Okay, so all right. So talking about this whole interval thing, we have this thing called the extreme value theorem that basically just says that if you have some sort of interval for a continuous function, there will be an absolute max and an absolute min somewhere on the interval. If you do have a starting point and an ending point, it has to. Okay, so let's jot that down, and then we'll use that fact to help us calculate some of these. All right, so here's what it says. So if f is continuous on an interval, call it AB, then f has both an absolute max and min on the interval. So, does that make logical sense to you? That there'd have to be a highest point and a lowest point somewhere if I gave this thing a starting point and an ending point? If I chopped a piece of a function off and just took that and used it? That's a good question. If it was just a straight line. In that case, if you're talking about just like a horizontal line, straight across, that's like the one situation where this gets a little muddied. In that situation, every single point on the interval is a max and a min at the same time. But other than that, you can find one distinct max and one distinct min, but yeah, that one's a little weird. Okay, and the other important part of this is this fact right here. The word continuous. Okay? It has to be continuous at every point on the interval. Okay? Think about that. If I didn't have every point on the interval being continuous, That would open me up to things like vertical asymptotes. If I had a vertical asymptote somewhere in the middle of my interval, could I have a max and a min? If it just kept going up or kept going down, would it ever have one point I could identify as a maximum or a minimum? No. Okay? So it has to be that the function is continuous at every point on the interval. Therefore, I can't have things like jumps or asymptotes or any of that sort of thing in the middle that get in the way. And then this thing can still work. Okay? So let's take a look at it, see if we can identify with a function what we've got here, and see if we can identify like what the max and mins would be and that sort of thing. So we'll start with kind of an easier function, one that you guys are used to, kind of know what the graph looks like. We'll just do x squared. Okay, so f of x equals x squared. And we'll put this on the interval -2 to 3. I want to see if we can identify what is the absolute min and what is the absolute max of that particular function on the interval -2, 3. So what do you guys think? How can I do that? Do I? Plug in some numbers?
Yeah.
Okay. So plug in what numbers?
Start with like 3 and then go down to 2.
All right. So f of 3 is what?
9.
9. And then plug in the -2. And that gets you... I think I heard somebody whisper it. 4. And then f of 0 is 0. Okay. Now, why did you pick 0? Why'd you plug that one in? All right, because you know when x is equal to 0 that this has a minimum, right? Because you know what this thing looks like, and you know the nature of x squared, and that if you plug in a 0, that's going to give you the smallest possible number you could get out of this thing, right? There are other functions where you're not going to know that ahead of time, and that's where it's going to get a little more challenging, and you're going to have to actually start using calculus to help you do it. But for this one, yeah, these are going to be some numbers of interest to us, okay? We know 0 is where it gets to its lowest, and then you guys plugged in the endpoints as well to kind of take a look and see where those were at. So knowing these three right here, we can get the max and the min right from that information, right? What is the maximum? 9. What's the minimum? 0, right? And if you wanted to, if you're a visual person kind of like me, drawing yourself a graph isn't half bad. So like, say -2 is over here. We're up at 4. 0 is 0. And then when you're out at 3, you're like over here somewhere at 9. So this portion of this parabola looks like this. So you can see here's the highest point, here's the lowest point. So it makes it a little bit more obvious. But yeah, you can get it from this information over here. So our absolute max is 9. And that's when x is equal to 3. And our absolute min is 0. And that's when x is 0. These get listed a little bit differently. Sometimes it just kind of depends. Sometimes you could just write these as ordered pairs. You could say the maximum is at 3, 9. Or the minimum is at 0, 0. Just list it that way if you wanted to. You really have to be careful about how the question is worded. And I didn't write this one out in words. But if it asks you what's the maximum or minimum value, what are they really going for? The y value, right? If they just ask you for what's the maximum or minimum point, then you can give them coordinates. Okay? Sometimes they might even ask, like, what is the maximum or minimum value and at what x value does it occur? In which case you'd kind of write it like this. So if you just write them all as ordered pairs, I'm not really going to care. But just so you know, like if you come up to a test or something and it's multiple choice or whatever, just the answers are going to be written such that it kind of matches the way that it's worded. But it's still the same concept, though, so I didn't want that to confuse you guys. Okay. So, how can we pull calculus into this to help us out? What do you know about derivatives at maximums and minimums? What has to be true about a derivative? Has to be 0, right? So we're going to use that fact to help us out. So, at local extreme values, okay, f prime of c equals 0 if x equals c is a min or max. So if you don't know where those minimums or maximums are happening, okay, like in that parabola we started with, you knew that when you plug in a 0, you're going to get a 0, and that's the minimum, and that's safe, and because we know what the graph looks like. But if I give you something that's a little bit not as cut and dry, then you're going to have to go searching for where those minimums and maximums are happening, and so you're going to have to use the derivative, set it equal to 0, and then work backwards to check and see what x values are going to make this thing work. Okay? So that's what we're going to be kind of focusing on from here. So let's see, what's one I could give you guys? It's good. Do another polynomial. Are you okay? Okay. That's not good. All right, so let's say we've got this function, 1/3 x to the third plus 4x squared. And I'm going to put it on the interval -1 to 10. And let's figure out, find all local and absolute maxes and mins. Okay, so let's zoom that in just a little bit, maybe make it easier to see. Maybe. And these are still pretty fuzzy. Oh, that's a little better. Oh, sorry. Been kind of rough so far this morning that way. Okay, so the different places where we could have maximums or minimums then, we could have somewhere in the interior of the interval where the derivative is equal to 0 could be a max or a min, right? Because it could be one of those, local maxes or mins, that sort of thing. Or maximums and minimums could also happen at the endpoints of the interval. Okay? So when x is equal to -1, when x is equal to 10, that could be a local or an absolute, depending, as well. So we've got to test all of that and see. So I always start with the derivative and then worry about the endpoints at the end. So first, let's do the derivative of this function that we have here. So f prime of x would be what? X squared plus 8x. Okay. And I want to know, where is that equal to 0? I'm not plugging in a 0, right? It's not x equal to 0. It's where is x equal, or what is x equal to when this is 0. So that's what I got to do next then. So take x squared plus 8x, make it equal to 0, and then I got to solve that equation to figure out where these interior points might be. So how do I do that? You can pull an x out, yep. If I do want. So where is x equal, or what values of x work for this thing then? Right. Okay. So now look at my interval though. So which of those two am I going to use? Just the 0, I don't need the -8, right? Because that's outside of my interval. Now, if I had expanded my interval and made it a little bigger, maybe if I made it go from like -10 to 10, then I would use the -8, and that would count as one of them. But you got to be careful. If it's not technically inside your interval, you don't need it then, because I'm only concerned with numbers that are between -1 and 10. So I'm going to go with this one. Okay. So f of 0, f of -1, f of 10, those are all ones that I'm concerned with then. Okay? So we got to plug them in and see what exactly do we get out of each one of those then. So f of 0, go back to our original function. What do I get when I plug in a 0? 0. And then the endpoints of my interval, -1. Can we do that in our head? Or do we need a calculator for that one? I believe it's 3 2/3, yeah. Because you'd have 4, and then you'd have to subtract a third. So it's 3 2/3, yeah. All right, and then what about 10? It's going to be really big, right? It's going to be a max. Yes. For sure. Let me just, 733? Is that what you got? Wow. 733 1/3. That's what I got. Okay, so can we identify then what's a max, what's a min, what's local, what's absolute with these 3 points that we've identified as being our points of interest here? So what is each? First one is a minimum. Is it? It is absolute, right? Mm-hmm. So what's the second one then?
So how am I relative? It's a local minimum.
Nope.
Maximum.
Yep.
Because the last one was the minimum and it's lower than 90.
Right.
Yep.
What's this one?
Absolute max.
Good job, class. I mean, Rachel. Okay, now, if you have a hard time seeing why is it local or absolute or all of that, like I said before, you can sketch it. Now, I know the numbers are super huge, but it doesn't mean you still can't, like, at least get a sense of where they are relative to one another. So, when x is equal to 0, we're at 0. When we're at -1, we're up at, like, 3 2/3 here. And then when we're over at 10, it's up at this like 733 business. So in any event, it's kind of coming around like this. Okay, so relative maximum, right? It's the largest thing around it, but it is definitely not higher than this other one. So it's only a local maximum. And then down here, this is the absolute minimum because nothing else is getting lower than that. And then over here we have the absolute maximum because nothing else is going to be higher than that. Okay. Now, what if I did make my interval bigger? Okay, what if I did have negative 8 in there? What would this function be doing when it got down to negative 8? It's going to be another... It's not a local min. Wouldn't it have to do something like this and come back down? Making this a what? A local max. Right. So this would be a local max. This would be a local min. And then and it depend on where I chopped off my interval. But I just wanted to show you guys that at least because do you see how my original function was cubic? And if I let my interval get big enough, I'll be able to see this whole thing with its maximum, its minimum, and then it keeps going. So what I'd like you guys to do is graph this thing on your calculator real quick, this 1/3 x to the third plus 4x squared, and take a look at it. You should see a little maximum at negative 8, and you should see a minimum when it's at 0. Just to make sure that we did all this calculation stuff correct, and you can kind of verify that. But be careful you don't graph the derivative, you just graph the original function. 1/3 x to the third plus 4x squared. Yep. Yeah, you're going to have to make your Y max, like, really big. Like, I'm thinking 100, maybe? Yeah. Yeah, that's what I did. And you can see it pretty well. So, what we're looking for, though, like I said, when x is negative 8, you should see a maximum. When x is 0, you should see a minimum. Because those are both the two places where the derivative was equal to 0. So, yeah, I made my y max like 100, and I'm getting a graph that looks kind of like that. And that verifies it. All right, you guys got any questions on that one before we move on? We're good? All righty. Let's try another function here. Do the same kind of thing. Right. So we're going to look at the function f of x equals 1 over the square root of 4 minus x squared. The last one we did was polynomial. So we kind of had a sense of what the graph should look like. My guess is on this one, you guys probably don't know what 1 over the square root of 4 minus x squared looks like. Just throwing it out there. Probably not. Okay. So we're going to try the same analytic methods, which is the by hand stuff with the derivative. See if we can identify where this one has some extreme values. And I'm not going to put this one on an interval. Okay. Now, that being said, this particular function does have a domain that we're going to have to stay within, which will help us out a little bit. So we know we can't go outside of those numbers at least. So look at the way that function is put together. And what do you suppose its domain needs to be? What are x values that are going to work when we plug them into this one?
2 will not.
Okay, 2's got something to do with it. What's going to happen when we plug in a 2? You get the square root of 0, but that's in the denominator, right? So can we use 2? No. Or negative 2, right. But what about like the numbers in between 2 and negative 2? What if we made them smaller? Would that work then?
You can't just square root of like 3.
Well, remember, you're going to square x first. So what if, let's say x was 1. Can you plug in a 1? So that does work, right? Can you plug in a 0? Does that work? Sure. Negative 1? Yep. So anything between negative 2 and 2 works. Now, as soon as you get bigger than 2 or less than negative 2, then you're having problems again, right? Because then you're taking the square root of a negative number by the time you're done. So our domain, not including, is that. Okay, so let's do our derivative here. Now, it might make things a little bit easier to rewrite this equation like that. It's a square root, it's in a denominator, so it's a negative 1/2 power. Now what method can I use to take the derivative? Is this a product rule problem now? Is there a product of two things right there? Is it a quotient rule? No. Chain rule. We are going to use the power rule with a chain rule, though, because take a look at what's being raised to a power, and it's a derivative, right? So we're going to do a chain rule to do this. If you don't, well, that you're still kind of in trouble, because you'd have to do a quotient rule here with a chain rule involved, and so this is still going to be easier, I think. All right, anyway, so derivative. So we drop the power down in front. We're going to leave this alone for now, 4 minus x squared. What's going to be my new exponent? Negative 3/2. And then multiply that by the derivative of the inside. This is like, remember in this one, our u would be this 4 minus x squared. So what's the derivative I'm multiplying by here? Negative 2x. Okay, so simplify this thing up just a little bit here. Here's what we got. Yeah, I like it. Prime of x. The negative 1/2 and the negative 2 will both cancel. So we'll be left with just x on top. And then it's going to be 4 minus x squared to the 3/2 on the bottom. Everybody follow how I did that? Turned it back into a fraction. Got rid of the negative exponent. 2's canceled. Negatives canceled. Say what? Okay, yeah, okay. All right. So, now remember, what am I doing with this derivative? Set it equal to 0, right? We need to figure out what x makes this thing equal to 0. So if 4 minus x squared to 3 halves equals 0. There's only one number that's going to make that happen. 0, right? Fraction equal to 0, only the numerator that's going to affect that, right? Denominator could be whatever it wants to be. As long as the numerator is 0, this is going to come out to 0. So the only solution to this is x equals 0. Another way of looking at it is you could take this entire denominator, multiply it over to the other side, and it's still going to be 0, right? So then x equals 0 when you do that. So our solution is when x equals 0. So then the question becomes, is this a maximum? Is it a minimum? What's going on? Is it absolute? Is it local? How might I figure that out? Because we don't have any other ones to kind of like put around it, right? We don't have any other maxes or mins to plot if we're going to make a little graph or something to kind of check. Do what? Can't do those, right? The endpoints don't work because they're not part of the domain. What other numbers could we try to put in and see maybe what? Could try like a 1 and a -1 maybe and see what happens with those. Plug in the 0 too and see what that... So just start testing some points around it to kind of see what's going on here a little bit. So that's what we're going to do down here at the bottom. So we'll do, first of all, 0. What does that get us? I heard somebody whisper it. It's 1/2. Okay. So f of 0 is 1/2. All right, well, let's try like f of 1, f of -1, see what happens with those. So be 1 over the square root of 3 for both of those. Then the question becomes, what's bigger? Or 1 over the square root of 3? Is 1/2 bigger? Try the calculator once. 1 divided by 2 is 0.5. 1 divided by the square root of 3. What's that? Yeah, it's 0.5. Thanks, that's good. You're fine. 0.577-ish. So 1 over the square root of 3 is actually bigger. Because the square root of 3 is smaller than 2 when you divide by it, it actually makes a bigger number. So I'm going to graph this thing. When I'm at 0, I'm at 1/2. And then when I plug in my 1 and my -1, I'm actually up a little bit from there at this 1 over root 3. So this thing is kind of doing this. Okay, so this one critical equals 0, what is it? It's an absolute minimum, right? And if the question asks, what is the value of the absolute minimum, you could say it's 1/2. But that's where it is, at 0. So, just got one last thing I want to put out there for you, and then I think you guys are probably good enough to get going on this stuff. As long as you do your reading, you should be good. Just wanted to define, because I've used the term a couple of times now, a critical point. Okay. Now that has kind of its own little definition too, just so we're clear on what we're talking about with that. Okay, so a critical point is a point in the interior of the domain of a function f at which f prime is equal to 0 or f prime does not exist. Okay, so I'll give you a quick example of, like, the last little part might have thrown some of you guys, like, oh, where doesn't exist? When in the world could that happen? Well, minimums and maximums can happen sometimes where derivatives don't exist. Case in point, this guy. Absolute value. Does the absolute value have a minimum? Yes, it sure does. It's right there. Is the derivative equal to 0 right there? Nope. Okay, so it's not just where the derivative is equal to 0. It's where the derivative is equal to 0 or possibly where the derivative does not exist. Okay? So you got to be careful of that as well. So in something like the absolute value, you couldn't use that derivative test to figure it out, but if you knew what the graph looked like and you know, oh yeah, there's a corner there at 0, that could be a possible minimum or maximum. I got to figure that out too. Okay? We're not going to throw any like major with this just yet. Later on when we get into it's called the first and second derivative tests, then we'll start to kind of delve into this stuff a little bit more. But I want to at least have that out there for you as well. So it's basically two criteria that could happen. Either the derivative is equal to 0, in which case it's a nice smooth curve doing a minimum or a maximum, or it's the derivative doesn't exist where it could be a corner cusp, something like that. Those can produce maxes and mins as well. Okay, so kind of look out for those as you guys go. So I'm going to stop my thing here.